Welcome back. This is the fourth video segment for section 7.4, 7.5 collectively. I'm going to put these all together. I think we're probably going to be able to finish this material in a total of 5 sections. We still need to develop something called the dot product, and then we can finish with this sort of expository sort of interesting problem that that is kind of the culmination of this whole section, of this whole pair of sections. So let's kick on over here rather than just listening to me talk with an interesting background. Let's kind of be able to write some stuff down. So first, I think I've readjusted my document camera so you can see more what's going on. Again, I'm just going to keep 7.4 as we're actually well into 7.5. I think we're on page 8 now. Hope I got that right. Okay, if not, I'll just correct it after the fact. So here's a new idea. If you notice, we've talked about how to take a vector and multiply it by a real number. That's called scalar multiplication. We've looked at how to add 2 vectors. But the question might then be, how do we multiply 2 vectors? Is there even a process that's like that? And it turns out that the answer is yes. There are some fairly well-recognized ways to, quote, multiply vectors. But the problem is that we're dealing with what's called a vector space, which has two different things in it. It has scalars and it has vectors. And what we'll develop here is a process by which you multiply 2 vectors and you get a number, not another vector. There is something that you may see in like a physics 2 class, if you ever go on and do that, where you will have a different type of multiplication where you take 2 vectors and you actually get a vector out. So collectively, anytime you have a mathematical system where you construct a way to take 2 vectors as input and in some sense multiply them to produce a scalar, this is what's called an inner product. Now, for arrow vectors specifically, we're going to develop something called the dot product, okay, which looks an awful lot like multiplication in the sense that it works very similarly. So let me start with a vector that's represented in component form. So let's consider u equal to u sub x comma u sub y. And for illustration purposes, I'm going to remind you that that's also equal to the magnitude of u times the cosine of the angle of u, comma, magnitude of u times the sine of u. Now we could, oh, and I need to get my little brackets there. Now we could think about maybe doing some kind. Now remember, this is a vector. These are components of vector. These are real numbers, but inside that bracket, it's actually represented by u sub x I plus u sub y j, right? And if we wanted to, in some sense, maybe represent this in this form, we would have magnitude of u times cosine of angle u I plus magnitude of u times sine of angle u j. And then similarly, this is kind of where we're trying to get to here, is this. And then similarly, if we had, say, another vector v, which is just, one of the representations would be v sub x I plus vy j, which would be the magnitude of v times the cosine of angle v plus magnitude of u times sine of angle, sorry, not u, v, angle v in the j hat direction. Okay, so here's their 2 sort of Cartesian representations where we have magnitude and direction embedded in them. And you're asking, well, why in the world would we do all this? Well, just like we did before with addition, notice that what we did was we just kind of added the x components and the y components to produce the final result, which was, you know, let me just kind of recall this. So u plus v was just u sub x plus v sub x, comma, u sub y plus v sub y, right? This was how we did addition. But now if we wanted to do something akin to multiplication, it might make sense to work with these components separately, right? But they may not come out as a component. Remember what I said, the dot product produces a real number, not another vector. So maybe if we just think of this as being, you know, sort of the leg of a triangle, and this is another leg of a triangle, and somehow maybe multiply these together, you get exactly what's called the dot product. So u, and it looks just like a times sign, only in typographics, it usually is a little bit bigger. U times v, this is the dot product, is going to be equal to, well, u, magnitude of u, times magnitude of v, times the cosine of the angle, the direction of u, times the cosine of the direction of v. No direction, but no vector, no unit vectors here. And then I'm going to put on the next line, plus magnitude of u times magnitude of v times the sine of the direction of u times the sine of the direction of v. Now, look where this came from. This is just simply these two things multiplied together, lose the unit vector, that becomes this term. Multiply these two things together, lose the unit vector, it becomes these terms. Now, I want you to pause there a second and think about what we've got here. We now have what appears to be the products of the lengths of both these vectors, the products of the magnitudes. If we were to factor that out, what we're left with, u times magnitude of u times the magnitude of v times this product, cosine direction of u, cosine direction of v, plus sine direction of u, sine direction of v. And that should look very, very familiar. Because what that is that's a cosine A minus B formulation, right? So here comes these trigonometric identities back again, which is going to tell you that the magnitude of u times the magnitude of v times the cosine of the difference in the directions. So here we have the dot product by this sort of weird sort of calculation here gives you this formulation here. And so what the net result is that if you wanted to know the angle between two vectors, so let me just kind of draw a picture over here. If you've got two vectors that are, who knows what their actual directions are. If you just want this angle, so this is u and v, then you might just solve this equation for the component, or the difference in directions. So one of these formulations is to say, okay, well, the cosine of the angle between, that's this angle right here, right, is theta u minus theta v. It might be plus or minus depending on how that's calculated. But notice for cosine, you can easily insert a negative sign. You will get a positive number out of this. And if you don't get a positive number, then you get a negative number, you just change the sign because of symmetry identities for cosine. But this will simply be equal to the dot product of the two vectors divided by the magnitude, the product of the magnitudes of the two vectors. And this right here is a powerful equation that allows you to take the direction, to take some relatively easy things to determine and calculate the direction that's between them. Dang. So let me kind of back up here. So this was sort of the way to derive this equation. But the real question is, how do you calculate this dot product? And so let me move to another sheet of paper here and do this in a very, very specific example. So let's take let's take two vectors. We might be able to actually finish this right here. So let's I think page 9. So let's take two vectors. Let me make them kind of a little interesting here. So let's maybe U, V. So I'm just gonna try to make up some numbers for these that make sense. So let me start with U obviously has a negative x coordinate, so let me just say -2, 5. And V obviously has a positive x coordinate, so let me just say maybe 6, 3. This will turn out to be a, well, some kind of a, I mean, if we were to guesstimate what this angle is, it's less than 30 degrees. And this angle is around maybe 110. So maybe the difference between these we're expecting to come out is like 80 degrees or so. You know, just kind of think for a minute estimation. 80, maybe 110. You know, it's hard to say because translating from the picture that, but it's pretty close to, you know, 90 degree angle. But it could be a little bit more, a little bit less, just because my graphing technique is not spectacular, and translating it into simple numbers for these components is not an easy thing to do. Okay, so let's go back and look at this formulation that we have for the dot product. Now notice we started by saying maybe if I just multiply these two components together and produce this first term, and then multiply these components together to get the second term, then I get this result. But remember what it was I was multiplying together. It's actually ux times vx and uy times vy. So what we have is a sort of an alternate formulation for the dot product is that u dot v is equal to ux vx plus uy vy, which if you already have it in component form, makes it trivial to find the dot product. So in this particular case, u dot v is equal to -2 times 6 plus 5 times 3, which simply equals 3. Okay? So if we wanted to find the angle between them, we need to find the magnitudes. So the magnitude of u is equal to the square root of -2 squared plus 5 squared, which should result in the square root of 29. And the magnitude of v is equal to the square root of 6 squared plus 3 squared, which I believe is the square root of, let's see, 36 plus 9 is 45, which I can pull, let's see, is that right? Yeah, so 36 plus 9, 45, square root of 45, which reduces down to, I believe, 3 root 5. It doesn't, the simplification is not entirely necessary for what we're trying to do here. And if you wanted to find the angle, you could do that too, but that's such a laborious process that I'm just going to leave that alone. We would need to know, if we wanted to find the direction of these vectors, that'd be fine, but we're really kind of more interested in the direction between them. So recall then, the angle, the cosine of the direction of the angle between these two vectors, which could come out as a negative number, but then we would just change the sign, is the dot product divided by the product of the magnitudes. And if we plug these all in, we get something kind of a little bit ugly, but this is going to be equal to 3 over the square root of 29 times 3 square root of 5. And I don't need to simplify this because all I'm going to do is take the inverse cosine. And the hope is that that's actually that this is in the range, and of course it should be because we have a 3 over 3 here. So I'm ending up with just simply 1 over the square root of, well, 5, let's see, that's 145, I think, right? Because 30 times 5 would be 150. So back 1 off, square root of 145. And we can I don't know that we can actually necessarily simplify that because it's a prime number times a prime number. But what that we're doing here is we're verifying that this is in the range of inverse cosine. And it's in the range of cosine. And so we can actually take the inverse cosine of both sides, which in fact it is. So the difference in direction will simply be the inverse cosine of 1 over the square root of 145, which, if I pull out my calculator here, it's going to be pretty close to 90 degrees. I'd almost guarantee it. So 145 square root, take the reciprocal, and then take the inverse cosine. I get 85.2 degrees. Ish, close enough. So, like I said, we started with this sort of presumption of these, we drew some pictures. We presumed the components, which is clearly not exactly right, and then developed this alternative formulation. It was actually where it started, this formulation of the dot product in a much easier consumable form, then used the equation that was developed on the previous page to find the angle between them. And it turns out this is all internally consistent, and one of the great things about mathematics is that you can do things in different ways and you end up with exactly the same results. Like we could go back and look at, because the easiest way to find the angle between two vectors is to know their magnitude and direction, which is sometimes easier to work with if you're talking about a measurement. But if there's another context in which you need to know the direction between them, this is the way to produce that. Okay, so I think this one might be a little bit long, but I wanted to go ahead and finish this in one fell swoop. This is the end of everything in chapter 7. And if you want to take a minute to go back and review some of those law of sine, law of cosine relationships, there is some of that's mentioned in these sections because that's how the textbook is arranged. You do law of sines, law of cosines, and then you move into this vector stuff. But notice I haven't had to appeal to any of that to be able to produce this stuff. It's just basically we construct a mechanism by which we add and quote multiply things together, and we have some interesting results. So with that, I will sign off. I am going to put some stuff on Blackboard that is usually the last day that is kind of supplemental, not something that you necessarily have to watch, but if you get a kick out of this stuff and you're starting to see how big the world is starting to become, you might take a look at it. I do an exploration into spherical trigonometry, which is one of my passions, and you can take a look at it or not. But thank you very much. It's been a great semester, and I wish you all the best of luck.